Hey everyone, how's it going today? I found something the other day. Thanks for the raid comment. So I found something the other day called ProSonic. So I found this thing called ProSonic. It's on Bitbucket. Did you work out the angles? No, I haven't. No, that's still the goal for today. So I'm going to do, I guess, 2 streams on angles, which is not great, but yes, that's what we're going to be doing. So I found this code on. Oh, thanks for the follow. So I found this code on Bitbucket called ProSonic, and basically someone's taken the Sonic ROM and translated it over to C. I don't know how they did it, but this is the C code version of the Sonic ROM, of the Sonic 2 ROM. What I noticed was there was a lot of logic in here that was I think it was Sonic 2, is it? Maybe it's only Sonic 1. This might only be Sonic 1 actually, now that I'm thinking about it. No, Chemical Plant Zone. So this is Sonic 2. So someone has done Sonic 2. Yeah, so they've got a lot of go-tos. One of the things they did, I think it was probably by hand. Yeah, I think you're right. Yeah, it's as clean as what you kind of gonna get translating from assembly, like without going too far. Yeah, so it looks okay. There was a lot of what they did. I don't know if I've. Yeah, I don't have it here. Maybe I can come over here. So I did make some slight changes. There was a lot of this. Actually, no, not that part. There's a lot of here. If def enable logging, then do a log line. Then yeah, that's it. So they had a lot of that. So I deleted everything that mentioned enable logging, just because that was all throughout the code, and I just found it like really hard to kind of follow the code when I had to do an if-def in my head as well. I mean, it was only about logging, and I could try to ignore it, but it was a bit distracting, so I got rid of that. So, yeah, we don't need debug code. We can just read the code. So, hopefully, right, so my goal is to figure out the angles from, figure out what angle Sonic should be standing at as he's on the ground. And so, hopefully, instead of staring at the assembly code and trying to figure out from there, hopefully I can read this C code, which I think is a little bit easier for me to read at least. I think for everyone it's probably easier to read than the equivalent assembly. So hopefully I can follow this through and figure out what angle Sonic is at. Thanks for the follows. So yes, so I mean, this is gonna be interesting. So this is like the MD normal that I've been trying to write. I think I wrote something MD normal over in my code. I think this was the equivalent of MD jump. Probably a lot easier to read, just worry about inaccuracies. Yeah, but maybe reading the raw assembly is going to have worse inaccuracies. Yes, exactly. I've not been very accurate in reading my assembly, so yes, so I'd probably rather trust this than my interpretation of assembly. Thanks for all the follows. So I don't know. There's this thing called angle pause. I'm guessing. I mean, that's in this normal thing. Angle pause. So I'm guessing angle pause might be it. So I've only had a quick look at this. I've basically deleted the logging and then had a quick look. So I'm not very good at. I don't know where everything is yet. So Sonic angle might be. That looks good. Sonic angle. What's that? So it gets the angle. So what's D2? D2 set up here. So I mean, like this is the type of it accesses RAM F76A. So yeah. Cool. Thanks. So yeah, like I don't know what this F76A is. What the hell is that? So that's the type of thing where it's like, well, names could be useful here. Because I have no idea what... It's just accessing a part of RAM. It's just giving a name to a part of RAM. Ah, yes, thank you. I always forget that. I do always forget that, thank you. One thing that actually... So, they were trying to re-implement... one of the interesting things about this ProSonic is that they so they started porting over the assembly, and they got so far with it. They had to go at doing that, and then what they did is for some of it they didn't convert over, and so what they did is they included an interpreter. So what it would do is for chunks of the code that they didn't translate over, they would actually call out to the Sonic 2 ROM and actually like interpret the assembly. Like they'd actually have like they actually had like an emulator for the processor, and they just ran that part of code, and they had like a fake RAM that actually pointed to the RAM that they set up in here. So it's actually interesting because it actually had like C code that was calling into the Mega Drive processor, the Motorola processor, running the assembly and then jumping back into the C code, which was an interesting way to do it. So it's using this angle D2. And then it jumps down here. So I guess what I need to do, right, is I need to find out like the first thing I need to do is find out the angle. So there's the angle data in the actual level. So in the level, if we go to S2, so what is it, curve? Is it called curve and something? Curve. There's a file in here, I'm trying to figure it out. It's not in there. Is it collision? Yeah, in collision, isn't it? It's in collision. Curve and resistance mapping. There we go, curve and resistance mapping. So this is the for like the level references this angle array. So this array that comes from here, it references that, and basically the index of the the index of the actual 8x8 block that you're inserting into the map, like into the level. It will like the index will be the same index in this this curve and resistance mapping. So then it accesses that and checks out what the angle is. So I don't know if this uses the curve, where that mapping comes from. Yeah, I don't know where it actually reads in that data. So I guess that's kind of what I want to go. I want to go from this, oh, there we go, call curve map, not curve. No, there's not even an occurrence of curve. So I'm just trying to figure out, like, there's somewhere that must read in this, this curve map, and that's where I was getting stuck with last time, I think. So this is the Yamaha, this part that's showing up here. Yeah, this is the Yamaha emulator for the audio. I mean, maybe that's what we should do for now. Try and emulate the audio Like, because that's going to be another very complicated thing, I think, to be able to actually play audio. Like, to re-implement that part in Haskell, I think would be super, super complicated. So I think we'll just emulate the audio when we get around to it. Yeah, but I want to see where, like, the curve stuff, like, where the... I guess what we'll do is we'll go backwards. We'll find out where this is used, the call curve map. We'll have a look at where it's used, and then we'll see the equivalent. So there's find wall 2. Let's go back to ProSonic and go find wall 2. And hopefully that will reference something. So it does a find tile, and eventually collision address. There's the collision address, so there we go. That's that part. So then it goes down a little bit. Block solidity, what's that? And then it does an address table. Here we go, bat though, that's called slope. Oh, they must call it slope in this. They call it slope, I think. I don't know why it's called bat. What's bat stand for? But that does look like the slope data. There we go. Okay, so they got the slope data here, I think. Cool, okay. So I guess I want to see where the where that's loaded, because I think that was the original problem I was having, trying to go from, like, trying to actually load up the data. Here we go, create bat. Is that... It looks like it's pre-processed. So I see it specified there, but I don't see it implemented. What? So there's this function declared. Oh, I guess it's not actually referenced. So C's like, well, whatever, you declared something, but you haven't implemented it. It doesn't matter. Okay, so it's not used. Okay. Okay, so I don't think that's useful. Okay, so we'll go back and we'll search again. Here we go, zone. Let's go zone. So it is different because this is not actually loading it from like a ROM. Like, it actually has like a preprocessor, it looks like, that it goes through and creates these .bat files or bat.txt files. So this is different. So the way that they index in that is probably not right. But I guess it does tell me that what I have to do is load it up somewhere and store it in a format that is addressable like that. So I mean, I also don't care about the format. I also don't care about, like, I can load it up wherever I want and put it into whatever Haskell data structure I want. Like, I don't have to even be restricted to an array like they've done here. I don't know where they've... So they're changing the address table. Oh, here we go. Here we go. That's what they're doing there. So they're reading the file size. And they go through every character in the file, read off the character, and then they look at the address table and put the data at that location. Okay, so they just re-index it. So why do they have this address table? Don't know why they've got this address table thing. I know that they're re-indexing it, that's all I can understand. So they're re-indexing it for some reason. File size data. The address table, so it looks like it's for the file count. Okay, well, okay. I don't think this is very useful. I don't understand why they're what the address table is. I can't figure that out. So what I understand though is that they are addressing this bat thing by these. So these are useful things. What's this bsol? bsol. Don't know what bsol could stand for. bsol. So look at the bsol address table. I have no idea. Oh, maybe it's block solidity. Yeah, block solidity address table. Okay. So I'm guessing bsol address table is like, yeah, the address table for this block solidity. So basically, they're trying to get out the they've got the the block, the number, like the block number that you're like when you're colliding with something. So they get out the collision address, like they get out what you're colliding with or whatever they're looking at. Get out the block ID, and then I think they're referencing the block ID there. So then they get out like the ID of so I guess out it looks like the block solidity. Oh, but it's the address table, so I don't know. What's the address table? So it looks like the solidity is the same as, like the solidity index might be the same as the slope index or the curve index. So A2 here is the collision address that we just got up here. Okay, cool. So that's the collision address. D0 I don't know. D0 something. So that, I guess that corresponds to that. So this part corresponds to that part. So I don't know. They read out this slope thing, which we've called which is called curve map in the actual assembly. It's called bat over here. What I wish I could find. I'm just trying to understand the C code right now. I'm trying to figure out. Well, what I want to know is like where this bat is coming from. That's really what I want to know is like where so it looks like they generate this bat file in some way from the actual Mega Drive ROM. And so what I'm trying to figure out is how do they read in the Mega Drive ROM to generate this bat file? I can understand how it's indexing. That's fine. I don't mind. Like I can go backwards from how they're indexing it. What I want to know is how do I go from the ROM to this thing? here we go. This might be it. Here we go, yeah. This looks like a level editor. Yeah, it is. Okay. So this is where they're actually editing the data. Maybe they never actually loaded in the, maybe they never loaded it in, maybe they just made their own data structure and then allowed people to edit it. Maybe that was it. Maybe they never loaded in the Sonic ROM. Because this is under the tools, so this is just, I think this is, yeah, this is just an editor. So maybe they just supplied an editor and they just let people, like, well, maybe they just recreated a level using the editor rather than use, rather than actually read the Sonic ROM. Block attribute table. Block attribute table. That could be it, block attribute table. That would be it, wouldn't it? Because it is block attributes. Thank you, that was useful, thank you. Okay, so I'll, yes, thank you. So that's block attributes, and what was it? There was bsol, which we figured out was the block solidity, I think. Cool. Because if we go back to the here, it's actually using the block solidity address table to talk to the bat. I mean, maybe that, I don't know. I don't know why it's using the block solidity to talk about the slope, the block attributes, but it is, I think. Okay, so block attributes. What does block attributes have? It's a char. Great. Okay. Okay, that doesn't help very much, but oh well. Doesn't help, that's just a char. Okay, so what I'll do anyway is, I was thinking I'll just load up the data. I'll just load up this curve map that we've got. Curve and resistance map. So I was thinking we just load that up. But then I don't know what to do with it. I just don't know what it represents. Like, I know that I think it's indexed by the block that we're on. I just don't know what the number represents. I've had a look and tried to decode it, and I just don't know what it represents. But I guess we can have a look. So I've got somewhere offsets. Here we go. So that's the collision array offset, and it looks like we're doing a binary include here. So I think. I just don't know what start address is. What's the start address? I know the end address because it's doing a binary include here, and it's doing a binary include here, so I'm just guessing that it ends at the same point that starts. I just don't know when it starts, when the call curve map starts. I guess what I could do is actually search the binary. How do I do that? So I've got that, and I've got my ROM somewhere. Where do I have it? So I've got these two files. I want to see where this file, where the first one occurs in the second one. Does anyone know how to do that? I'll just use Emacs. This is the Sonic 2 ROM here, and I'll just search for this FF. There we go. That's where it is. Cool. So this is the data for the curve mapping. Why are you clicking for swapping workspaces on your tiling WM? I'm not clicking. So this is I3. So I'm just going to print out this data. I don't know what we've got here, but I'm going to print it out. Just make sure that it looks right. Let's have a go at that. I'm probably printing like some big binary string right now, which is okay. Yeah, there we go. Okay. So that is the curve mapping data. Looks quite big. That does look quite big. Why? Oh, I've messed up somewhere. Ah, how did I do that? I did mess up there. I don't know how I did that. Why is it off by... What did I do there? I added another 0 on and then I deleted 2 zeros off the end somehow. I don't know what happened there, but okay. That should be right. That looks right to me. Cool, okay. Like I did just double check that. Like I did print it out to double check it. Okay, hopefully now I should have something that looks a reasonable length, and then we can start. I don't know, we'll look. Yeah, there we go. Cool. So now we can. So these are the values. I don't know what they represent, but I know that when you index them, I think you get a byte. You get a word out. Is it? A word corresponds to each block or something. How many are there? I was clicking for the hex. Where's the curve? There we go, curve end. Assume I picked Sonic 2 for lots of reasons. Were there any technical reasons for picking it over Sonic 1? Over Sonic 1? No, probably not. Sonic 1 probably would be more simple. Yeah, I probably should do that. There's one interesting thing. There is one interesting technical thing about Sonic 1, which is that it didn't include anything to deal with PAL versus NTSC regions, and so Sonic 1, the way I've played it was always very... I didn't realize this at the time, but when I was a kid, when I played Sonic 1, it was actually like, I don't know, I can't remember the exact percentage, but it's like 15 to 20% slower. I always played it because I was playing it on a PAL system. So That I guess there is a technical thing there, which is like, I don't know if I were to emulate Sonic 1, I don't know which way I would do it. The way that I grew up with Sonic 1, which is like 20% slower than what it was actually meant to be, or if I'd actually emulate it to how it was meant to be. I don't know. I'd be conflicted on that. It's actually interesting, like, when I went to play Sonic 1 on, like, a recent emulator, I'm like, this doesn't feel right, and it was because, yeah, it's because I like, on a PAL system, like, they didn't actually do any, changes, depending, like, they just kind of synced it to the hertz, and so I don't know if everyone knows, but there's, like, the difference in hertz between PAL and NTSC, so, yeah. And so they just synced it to the actual, to the clock rate. And so when you're playing on a slower system, the game actually went slower. Whereas in Sonic 2, they worked around that. So when you play Sonic 2 on an emulator, it doesn't feel any different to me. It's like Sonic 2 is just Sonic 2. Whereas Sonic 1, there's two, it feels like there's two different Sonic 1s. Even though there was only meant to be one. That's not really a reason why I didn't choose Sonic 1 though. I like Sonic 2 a lot more. That's basically it. And Sonic 3 I really like as well, but it's a big game. Sonic 3 was massive. Whereas Sonic 2 I thought was a lot smaller, so it just seemed a bit more achievable. Also, I think Sonic 2 and Sonic 3 are a lot more similar than what Sonic 1 and Sonic 2 are. Mostly nostalgia, exactly, yeah. But I do think that Sonic 2 and Sonic 3 have a lot more similarities in, like, I mean, for every game, they just took the old game and then they just added onto it. With Sonic 1, Sonic 2, they took Sonic 1 and then just added onto it and then manipulated it in different ways and made Sonic 2. But they did make quite a few changes between Sonic 1 and Sonic 2, and I know they did for Sonic 2 and Sonic 3, they made some changes as well, but I don't think they were as massive as what the changes were. Like, they changed a lot of, like the whole level format was changed between Sonic 1 and Sonic 2, whereas in Sonic 2 and Sonic 3, I think the level format is mostly the same. Although I think that they changed compression on some of it. But I mean, if we do things right in our implementation of Sonic 2, to change the decompression of levels should be nothing. It should be basically I change one line of code. If I do things right, that's how it should be. But the actual underlying format is the same. I think in Sonic 1 they use 128 by 128. Basically the blocks are a bit bigger, and so it actually changes a lot of things, like how you index into things and that. So they had to change that whole thing when they went from Sonic 1 to Sonic 2. Okay, so I've got the curve and resistance mapping, and I am printing it out, and it looks like that. I don't know what those represent, so I don't really know how to decode it, and I guess that's what my goal is to figure out. So I've got the core curve map. We are referencing it. Well, I guess the ProSonic thing I was excited about because I thought that ProSonic would actually be able to tell me how to use this core curve map, how to actually index into it to be able to use it, but it looks like they don't actually use the underlying Sonic 2 ROM like I am. They don't even seem to have any logic to load it up like I thought they would have. It looks like they've just got a level editor to be able to define their own things. So, yeah. It does, like, one thing that, well, I mean, they're using this block solidity, and then they're looking into this address table, and I'm like, okay, well, that seems right, that seems cool. I don't know if that's the same thing as what they're doing over here. What architecture is this? So this is M68K, the Motorola 68000 processor. And that's the disassembly that I'm reading here. Over here is like someone's hand ported it over to C, and then I'm hand porting parts of it over to Haskell. So I'm just comparing all three of these to try and get to a good point. So we've got the pointer there. A2 is this pointer to the collision data. So why is it... I think this is slightly different here. So A2 is the collision address pointer. Anyway, let's go the other direction, right? Let's, instead of looking at where it's loaded, let's look at how it's used. So A4, let's look at how A4 is used in the C code. C with a bunch of go-to labels. A4. So I see A4 being updated. I guess then we have to look at where it's being used later on. Okay, there we go. So we do a find floor, and then we store A4 into this RAM, into the RAM there, and then we access it again. So we store it and then we access it. And it's called D3. Okay. Let me look at that RAM address. Okay, here we go, A4. So I see it loading things from RAM, doing a find, then storing it back into RAM. And then the uses of that RAM address seem to be just to do what? Just to load it up. Here we go, D2. Here we go. Okay, so it loaded up the byte, and then, okay, so angle, here we go. So angle is what we loaded up. So when we get the curve, so it gets the byte out of this map, and then it stores it in this P angle, where P, I'm guessing, is the player. I think P is the player. Yeah, there we go. On init player. Okay, so P. Where's P come from? Player P. Okay. Okay. So this is the big struct that represents a player, I guess. This is the big struct that represents a player. Okay, so it's got all these things. Okay. Player name, character, sidekick, got input, velocity, position. Okay, so this is similar to a lot of the things that I've written in our player.hs. So we have a lot of these. We have velocity, radius is in here probably. Yeah, radius. Top speed, acceleration, I'm sure is in here. Here's inertia. I've got inertia somewhere. Yeah, player inertia. Cool, okay. And angle. Do we have angle? We don't have angle. So we're gonna have to update something to have an angle. I don't know what data type to use to represent angle, but over here it's just using a char, which I'm guessing corresponds to a byte. Oh, they got a short here, so maybe it's a word. I actually don't know how they're using the angle, actually, so that's the... How are they using the angle? Not uncommon to use 0 to 255 as if it were 0 to 359. Yes, it's not uncommon because that's exactly what it's doing, actually. I think we noticed that. We ran the debugger last time, and we did notice that. We noticed that I was getting confused because I'm like, oh, 0, like, I was mapping the angles as I went around, and I was expecting 300, and I was expecting it to do basically 360. But I noticed that the number never went to 360. I was getting really confused, and I realized that it couldn't get to 360 because it was a byte, first of all. So, you know, there's no 360. But yeah, when it got around to like 240, it was like actually mostly rotated. So do you know, so if it's not uncommon to use 0 to 255 as if it were 0 to 359 degrees, do you know the mapping of that? How does 255 map to 359? What is the how do they correspond? What is the correspondence there? Forgot how people handle that? Okay. Yeah, I think we'll have to figure that out. So I think this is like what I was saying before, is how they've got a yeah, I think what they're like they've got a because they emulate parts of the code. Part of the code is emulated. Some of it's like, a lot of it is hand translated over, but some of it is not. And so I think what this code here is doing is they're setting up a big like, I don't know, like a chunk of RAM, and they're like mapping the RAM to these objects. And so here's where they're assigning like all the values in the RAM to the state of the game. So they basically get out the state of the game, store it into this fake RAM thing, put that RAM over into, like, they run the emulator and then they read everything back out. I think that's what's happening. So then they can kind of actually, that's interesting that they're doing like a calculation problems here. Maybe they've actually got a way of like asserting the result of one of their functions. That would be really cool if they did that. Assert that the emulated version updates the RAM in the same way that the that their functions actually do. That's an interesting idea. Like, it'd be cool if I could take my player.hs, serialize it to some sort of RAM, and then run the emulator, and then just assert that serializing it again is the same. Like, running my function, serializing it again is the same as running the emulator. That'd be a really cool idea. I'd like to experiment with that. But what I want to know is, like, so this is, I think main.hs has got all the rendering. So I would like to see the angle part, where they render an angle or something. Roughly 1.5 degrees per byte value. Would it be sufficient granularly to make the character angle seem like 1 degree granularly? What do you think? Maybe. Yeah. But I think we're right that we are using 0 to 255, so we're using a byte to represent the angle. So I'm gonna go with that. I'm just adding the angle in. So let's go with that. Whoops. Yeah, let's go with that. Well, we need to add the angle in anyway. We'll figure out if I think word 8 with the 255 representing 360. I think that's correct. I think that's what actually is happening. So I'll just add in angle as word edit anyway for now. We can change it anyway later on if we need to. Whoops. I've actually been playing around with VS Code. I was thinking about switching over to it. There is one problem with it, which is that VS Code sometimes it's just really slow. But it does have I've been using the Haskell IDE engine. Thank you, Miguel, for the follow. So I've been using Haskell IDE. I've been playing around with it. The Haskell IDE engine, and it's pretty good. I mean, I could use it in Emacs as well, but I kind of want to. What I want to do is, like, at work I teach Haskell quite a bit, so what I want to do is like have an editor that people are more familiar with than Emacs. Like, some people have turned up to, like, there's been basically 1 or 2 people that have turned up to class that have been willing to use Emacs, and they've been interested in what I use. And they like are able to set up their IDE in a way that is similar to how I use Haskell. Basically, able to get all the integrations working. So there's basically only been one person that's been interested enough to really do that for Emacs. So I've been thinking that I should probably switch over to something that's a bit more comfortable for people. So I was thinking VS Code. Okay, so we're gonna have player angle now. What I should do is, I mean, what reminded me of editors was I was just generating all of these, I was just updating all these lenses by hand. What I really should do is have some template Haskell. I should be able to say make lenses, you know, player. I should be able to press a button on that and have it all generated for me, and just spit it all out in there. Because I don't like using template Haskell, but I don't mind using template Haskell if it's going to generate a heap of code for me and just insert it into my file. So what I should be doing is working on Haskell IDE engine to automate that away, so I don't ever have to worry about it again. Each byte value represents 1.5 degree increments. Is this how you transform to byte angle values to real angles? I think so. Yes. I think so. Yes. I think that's right. So if we have, I think we saw like. I think we saw fairly often there's like 240, which is like, which was most of the rotation around. So 240, because we saw 15 a lot. I think we saw 15 a lot. I think we saw 240 a lot as well. So 15 was like when Sonic was facing, which was 15. 15 was when Sonic was facing downward. I think 15, like it was when he was facing slightly like downhill, then that was 15. When he was facing slightly uphill, I think that was 240. Is that right? I think that was right. So 240, and you're saying like 1.5 would be 360. So maybe if 240 was him being flat, maybe that was the translation. Maybe there is no 255. Let me have a go. I don't really want to start the emulator again. I hate starting up the emulator. It's too much. It is too much. 1.5 is too much. But it seems like the angle that was being put out was being put straight into the Mega Drive's video processor. 1.425. Yeah, okay. It could actually be. I guess it could be that. Because I think this angle data, so this byte was actually just being put out to the video display processor in the Mega Drive, and they were basically saying, draw this sprite at this angle, byte angle, and so that byte angle, you know, is 0 to 255, and obviously it means something to be 360. So I think the Mega Drive has a built-in idea of this byte angle concept. So what I could do is, what we'll do, let's have a go. Let's open up Firefox, and we'll have a look at Sega Mega Drive VDP. There is quite a bit of documentation about the VDP. mean, I'm not great at this low level stuff. I'm not great at this, but let's look at rotation, angle. No. No. Sprite table location. So I want like a document. I want some documentation on like I think I've already looked at this one before. I just want to know like the format that they expected in, or like the sprite attribute table. Coordinate, size, link field, because it's like a linked list, priority, color palette, flip, start index, and then coordinate. So they don't actually, the sprite attribute table I would expect to have like an angle in it, but I guess not. So I don't know how rotation was done. Patterns. Each pattern is that many bytes. They're mapped to display. Okay, so a pattern. Pattern is what I need to look at. Okay, so if I go back to that file I was just reading, which one was that? Because that one didn't look that bad. So if I looked at the... Was it this one? So if I looked at pattern... There you go, patterns. Pattern is pixel block made up of 15 colors. Okay, that looks like it's just pixels, so I don't know why it's talking about rotation. Pattern name. Yeah, I kind of expected sprites to have like the idea of rotation in it. Okay, here we go. It's just that the Genesis is not capable of scaling rotation. However, Genesis is capable of these effects through software programming by relying on its CPU, faster arithmetic, and the VDP's faster DMA. Okay, so rotation is actually done through software. Okay. Rotation is done through software. How is rotation done through software? How do you rotate a sprite using software? Is there a sprite for every... rotation? It's not true, right? No. It's not true. Because Sonic's got a running one. They haven't built in a running frame for every rotation. So how is it done? How do they do rotation? Show me an example of the rotation happening. Sure, like I can show you in the actual game. Is that what you want to see? I can show you in the actual game. Whoops. I garbage collected that. What did I do with that? There we go. .90 rotation, you mean? 90-degree rotation? Sorry, I'm not sure what that means. Sorry, I don't know why I haven't committed this Blastum. Like I made a Nix package for Blastum, which is an emulator that I use because it's got a debugger built into it. So I don't know why I haven't committed that. So let me just make sure I can build it. Well, looks like I don't have the expression anymore. I don't know what happened to it. I thought I committed it as a branch, but I can't find it. No. Damn it. There is another emulator. What's another emulator for Linux? There we go, Gens.js, let's try that one. What? Oh. There you go. Let me build this. Alright, we'll have an emulator in a couple seconds. Sorry, I garbage collected last night and lost the Blastum that I was using. I will package it up and put it into Nix packages though, because it's super useful to have like a Genesis emulator with a debugger built into it. So the rotation is basically, I can probably show you on it. It might even have something, yeah. Yeah, so you've kind of got like, I don't know what that's about, but basically Sonic is walking and then he kind of goes up like one of the loops in the game. Well, half of these aren't actually Sonic 2, and so I mean this is a little bit of an example. I mean this is Knuckles, but anyway, so walking up one of these, you kind of get airborne. So you notice how there's some rotation on there. Or here, when you go up, you actually get rotated around this thing. So it's just mean, it's all throughout the game. I mean, when they wrote Sonic 2, they were trying to take advantage of the Mega Drive's capabilities or the Genesis's capabilities. So they really focused on the on this angle thing, because that was supposedly a very new thing at the time, being able to rotate a sprite around. I guess maybe because they did it in software or something. Here we go. Here we go. So you see Sonic's walked around the loop, and then he's there. And so he rotates around the whole thing. It's not super smooth. It's not very smooth. Like you can kind of see that it goes in increments as he's rotating around. It's not, you know, very smooth 360 kind of 1 degree changes or anything like that. It's kind of like he's going up and then he's like 15 degrees and then 30 degrees or something like that, and just kind of goes up in increments. I'd like to show you, but I'm compiling an emulator. I thought it would be cached. Here we go, there's another one there. So he's kind of rotating around. Now, I did have from the last stream. I was debugging that, so I was kind of like stepping through, and we did see values. I think up to 240. Okay, so I think it might be emulating. Okay. So I am actually on an angle right here. I'll take my headphones off. So I am actually on an angle right there. So Sonic is actually on an angle right at this point. It just doesn't really render, but he is on an angle, and you can tell he's on an angle because you've kind of got like it's slower to go up and faster to go down. I don't know if you can really notice that there, but you can kind of feel it. Like it's slower to go up, faster to go down. And here you can there isn't actually an angle here. It's just, there you go. So he starts showing about there. But he is on an angle here, and that affects where you jump. So you notice how when I jump, I'm not going straight up like I am there. When I jump here, I jump backwards. So there's a couple of places where it comes into effect. It's not always visible, and even though Sonic's on an angle, it's not actually always visible. And so I don't know, maybe that was an optimization of some sort. I don't know. If it is happening at software level. Let me see if I can show it off a bit better. I'll go around a loop in a second. Falling seems quicker than jumping. I'm not sure about that. Maybe. Yeah, so here's the thing. So Sonic can go around the loop. Forget enough speed. Go around. Goes around. You can't really see it when I'm in a ball, actually. So it goes around like that, and so you can see that it's not super smooth. Like, he's not going around like every degree. You can see kind of, I don't know how many rotations that was, but they're like how many increments there are in there. But it looks like we go about, I don't know, 45 degrees. Yeah, it looks like it is about 45 degrees, doesn't it? Perhaps you only need 8 different sprites for rendering. The actual degree values corresponds more to physics. Yes, yes, exactly. The angles, the actual underlying angles, do correspond more to the physics. So I think there is more than 45 degrees in the, like, yeah, there's definitely more than 45 degrees. Like, because you stand here, you do go back a little bit. So I think it does actually have like more than the idea of 45 degrees in the underlying data, and it's just rendering only has about 45 degrees. I think that's right. Oh, cool. There's an image there. Cool. Thank you for that. How do I exit the emulator? Okay. Let me look at this. There we go. Yeah, so that's the type of thing. I think the visual rotations are always 45 degrees. I think you're right, yeah. I don't think I've ever noticed that before, but I think you're right, yeah, 45 degrees. So thanks for that image, that's useful. So yeah, so I think it is only 45 degrees. So, what would be the implications of that? Maybe they've like pre-rendered the Sonic running or something. Because I think in the image, in the sprites that I've loaded up, I don't think they have the idea of, I don't think in the underlying sprite there is the idea of each image but 45 degrees rotated. I don't think they've done that. I think that would probably take up way too much RAM in a way, like, or way too much too much of the ROM. They were really trying to save, data on the ROM when they did that. Especially since what's actually interesting, one thing that is probably not really known is that I could check. I've got most of Sonic's animation and stuff loading up alright. It's most of it. I think halfway through it's kind of broken, so it's not. I can't 100% check. I can mostly check though. I could render it all, but what I think is, what a lot of people don't know is that Sonic's animation is Sonic's sprites are actually uncompressed in the ROM. It's uncompressed just because they didn't want to spend any time decompressing it, I think. It was just so critical to the game that they left it uncompressed because they didn't want to spend any time decompressing it. So, I'm almost 100% certain that they would not put an uncompressed Sonic sprite, like they wouldn't put in the uncompressed version and also have it all rotated. I just think that would be just too much ROM that they'd be using up to do that. So I'm very, very confident that they haven't baked it in. So it must be doing something at the software level to rotate it around. I don't know what they're doing, but they must be doing something. It's interesting. I thought the Mega Drive actually had like a built-in capability of doing rotation, but it's really interesting to me that they actually just have a fast processor enough to be able to handle the rotation. I do wonder if they pre-render it into RAM though. I don't know if that's a possible thing that they could do. But yeah, I guess what I would like to see is like some rendering logic, I guess. So I guess screen scaled sprite data start. Art uncompressed Giant Sonic. So Giant Sonic. I think Giant Sonic might be like at the beginning of the game, but maybe not. Yeah, Sega screen. Okay, yeah. So Giant Sonic is at the beginning of the game. Okay, cool. Thank you for the follow. VDP, control VDP. I'm just searching VDP through, like VDP is the video display processor, so it's like where the where the code actually like should be interacting with basically the graphics card. The Mega Drive's graphics. So I'm searching for VDP just to see if I can figure out where like angle stuff is handled. Like maybe before they do VDP, maybe they calculate angles and then manipulate graphics in some way to be able to handle angles. Thank you, Pedro, for the follow. I guess what I want to see is like where Sonic is actually rendered. Maybe. Show graphics, plane map to VD. I don't know what the plane map is. All this to figure out what rotation means. I think when I opened up the emulator last time, I think I was trying to figure out what. Actually, what we could do is look at the curve and resistance mapping data. So this is 255, 255. What's E0? Found an article that talks about the do's and don'ts of using byte to represent degrees. Oh, okay, cool. Let me have a look at that. Thank you. Let me load that up. Alright. Right. Okay. I do remember, like, so if we look at the Sonic hacking guide, is it this thing? Oh, what? Check out that. I probably should have been reading this hacking guide a while ago. Okay. Okay, so this has got rotation data. Okay, so this, okay, we'll look at this in a second. So this is interesting. Maybe it does have them pre-computed. Maybe I would expect not, because I thought it would take up way too much data, especially since Sonic is uncompressed. Maybe I had a bad assumption. Well, let's verify that in a second. I do have Sonic's sprites being loaded. I think halfway through I've got a bug somewhere, so halfway through they get corrupted. But I should be able to load up a good chunk of these, so I'll have a look. I think rotating sprites at most angles will look very bad due to subpixel interpolation errors. Yeah. So most should be pre-rendered. That is a good point. That is actually a really good point. It would look bad, wouldn't it? It would look bad, so it would be, yeah. That is a good point. Anyway, okay. So I think we've figured out that then. We have to figure out, I guess what we have to figure out is how to go from, so I guess that's why we're not actually doing rotation in the software. We're actually probably just using the angle to calculate which sprite to show. Okay, so we can look at that. There was also another thing which was, what was it? There's something here which is about the has a section on SNES mode 7. Oh, cool. It must not be this thing. It must be this one. Here we go, collision format. Okay. So just seeing this image remind me of one of these images. This. So it says here, Sonic 1, the representation in Sonic 1, the representation of angle data, is that if you see 90, so if you see hex number 90, hex, OX 90 in the angle data, so in this angle data that I've loaded up here, so if is there a 90 in here? There's no 90 in there. But if we saw 90 here somewhere as a byte value, if we saw 90, then what that means, supposedly according to this thing, is that you've got a line from 9 to 0, and then you calculate the angle based on that. Supposedly that's what the format is for Sonic 1. When I was looking at it, it didn't seem to make sense. I was running through these numbers and trying to correspond them back to the blocks that they represented, and these didn't make sense at all to me. Like having, I think D0 or something was like kind of like an angle down, like it was going from D to 0, but the actual thing was basically flat. So this might be the case in Sonic 1, I don't know, but it doesn't seem to be the case for Sonic 2. It's just that this thing over here reminded me of this. So I think Sonic 2 actually just has, I don't know, just like a map of these. I think these are actually like the angles, the actual data that we have. If you can flip sprites in both axes, you don't need all 8 directions to be rendered. I think 90 degrees can have lossless. Exactly, yeah, that's exactly the case. That's exactly what's happening. I'm sure of it. So they just flip it. They just flip it. Yes, and we can split sprites in both directions. That's true. So yes, so you can take most of these and just flip them to get the other version. Yeah. Yeah. So I think they've only got, well, why do they have Sonic upside down there though? Because what would make sense would be, yeah, you go up to you do like 0 rotation to 90 degrees, and that would be it, right? You do it to there, and then you just flip all the rest of, you flip to get this one. I don't know. Well, okay, let's have a go at rendering all of our sprites. I have had code to do that before, so it's got the Sonic's palette, got the script, mappings. Yeah, maybe the images on that. Yeah, maybe, I don't know. Let's actually render what I have loaded up from the ROM, which is not complete, but it should be something. So what I should be able to do is actually okay, so it needs an animation script. What's the animation script look like? So that's how much time to wait between each one. So animation script, let's say, wait 1 frame between each one, and then we've got a bounded array, word 8, animation step, and so I'll just say animation next. No, we don't actually do anything with that. So I'm just trying to create a array of everything I've got in my array. this should work. Okay, let's have a go at that. Okay, and oh yes, in my main I need to update this to be start off at angle 0. Okay. Oops. Okay, I can run. Cool. How's it going, Light and Light? Okay, so hopefully this will show me every frame, like it'll just cycle through all of Sonic's frames. Hopefully. It'll look weird, but hopefully it should just show every Sonic frame. Man, it's not. It's stuck at frame 1. For anyone else that hasn't seen the game so far, you can move left, you can move right. It's got the idea of inertia and you can jump. And that's about it so far. And it's super weird, but it does things. And so I'm trying to get angles in there, so when you walk up here you can actually see angles. And when you jump, I want angles in the jump as well. And you can also jump into outer space and crash the game. Heaps of fun. So I'm not sure why that didn't work. Oh, I did 0. Oh, why did I do that? There we go. That's what I actually wanted. I meant to leave that off. I didn't want to put an upper bound on it. Okay, so now hopefully this will cycle through all of the frames of Sonic. Game is not total. Oh, I know. Yep. I need to be writing Agda just to... I need to be writing Agda next. Look at that. You can see where what I was saying about it getting corrupted. Okay. That's pretty good. So that's the game. Yeah, okay. Go, I think there's like 50 good frames. I don't know how many frames. Maybe, yeah, we'll go 50 good frames. I don't know how many good frames there are. Let's go about 50. So what you saw was it does look like we got some rotation there. Well, we definitely have some rotation. Yeah, we got some rotation. So it goes all the way around. So I think we did see, yeah, we saw that, didn't we? I'll make it display a little bit slower. Yeah, I'll go 5 frames. So I just slowed it down. So it shows, it should show each frame for 5 frames. Each sprite frame for 5 game frames. So yeah, you should be able to see this slowly. Yeah, there you go. Kind of slowly. There we go. 1, 2. So there you go. Yeah. So we do have that. So this is actually what we have in the game. So we actually do have the uncompressed rotation of Sonic in the game, and we have all of these degrees. So we've got a walking animation. We've got a walking animation on 0 degrees, walking animation on 45 degrees. Then we've got a walking animation at 90 degrees, then another 45 from there. I think that's the last one. Yeah, so 90, and then, yeah. Cool. Combine it with flipping to get the other orientations, exactly. That's exactly what happens. Cool. Okay, so that explains how we render it. Okay. So we got that part. We got rendering. Thank you for the follow. So we've got the we know how Sonic is rendered with angles. Okay. It's all there's nothing special about it. It's just built in. Cool. So I do have to fix that bug eventually as well, that Sonic is corrupted. I actually should file a GitHub issue for that. Okay. Oh, thank you so much for subscribing. Thank you so much. That's a huge help. Okay, we got the angles that we render Sonic at. We know that. Now what we need to know is like when you're standing on a part of the level, what angle is that? And we do have that information, right? We do have in this. This does represent the angles that we're pulling out. It looks like we're just pulling them straight out and we're just saying this is the angle that Sonic is at. We're saying that he's at EC, which I'm not sure quite corresponds to. EC. We're saying it's at 236, and that's the angle. E8 is that's an angle as well? Yeah. Okay. So I'm guessing article is kind of interesting. It documents all the content that is in the ROM and not used in the game. Oh yeah, cool. Okay, I'll have a look at that. I always like those type of articles. Yeah, it's the cutting room floor, isn't it? Yeah, that's a really good it's a good website. I like that. Oh, whoops, what have I done there? Let's put parentheses in or something. Put backslashes in or forward slashes. Here we go. Night vision mode. Interesting. Okay. There's some cool stuff in it. Yeah, like, they had a whole level, Hidden Palace Zone. If you actually play the, if you, Sonic 2, if you buy the game for Android, there's an Android port, an official Android port. It's actually interesting. The Android port was actually written by Sonic. The people that wrote it were actually people that kind of like made Sonic fan games. And it's really interesting that this is not actually the original Sonic 2 ROM. It's actually a re-implementation of Sonic. So it's basically what I'm doing. I'm re-implementing Sonic 2. They did it. They've already done it. There already is at least another implement. I mean, I don't know. I think other people have tried re-implementing Sonic 2 as well. But there is at least one other re-implementation because this Android port is not. It's actually a port. It's not actually. Well, I don't even know if it's a port. It's basically a re-implementation with all the original game graphics and that taken out and put into this and made into an Android game. So it's actually a re-implementation. It's not the original ROM. So that's interesting. And another thing that's interesting is that if you actually play this game, there's a part of the game that in Cave, what is it, Cave? I always forget. Cave Zone, Sonic 2. Mr. Cave Zone. In Mr. Cave Zone, there's a part of the game where like everyone basically runs into like a big hole. And what they've done is they took all of this this unused Hidden Palace Zone content and made it into a level. So basically, if you die because of the easy way to die in the game, like you fall down a hole that usually makes you die, you actually get sent to this Hidden Palace Zone. So I recommend the Android port. It's actually pretty good. It's actually made by some fans of Sonic 2, and they actually like have taken some of this unused content and put it into the game, which is really, really cool. Really cool. Wow, there's a lot of unused content. Okay, so I think these angles are straight up used. They're straight up used. And so what I think what we should do is just read this in. Let's read this file, like we're reading the file in. So we get the angle data. Let's index into it based on the block ID. And then we'll read that in on every frame. When we go to see what block we're colliding with, we'll read this in and then assign that to the player's angle. And we'll just start printing it out. So we'll just say what the player's angle is at all times. And then we can see what values those are. Let's do that. Okay, so I've got the curve mapping in there, which is curve and resistance mapping. I don't know like what I mean by and resistance mapping. Curve and resistance. So we're loading up the curves, block textures. So I wonder, so here I'm using the idea of a collision index. So every map, every level has like it's got its layout, but in the layout there's also sorry, not in the layout, but in the every level has like a collision index, which is like this block looks like, to collide with this block it looks like this, and so it's got where have I got it? Yeah, so this is the collision format, right? Do they have images somewhere? I thought they did. Here we go, collision block reference chart. So basically what they do is these are all the different collision data in the game, and these, you know, they've got 255 of them, well 256 of them. And what it does is it remaps for every level, it maps onto this onto this data. So it maps. So if you've got like a block that looks something like that, it will say map that block. I don't know if they've got that data here either. I'd like to see all of the data at once. Oh, that's just where it was. Okay, yeah. Here we go. Here we go. No, that's not what I wanted either. I feel like they do have... I'm sure I've seen it somewhere. So this is the this is the 128 by 128 pixel chunks, they call it, chunk. And so each one of these chunk has an 8 by 8 pixel. Sorry, it has 16 by 16 pixel. What do they call it? Do they call those blocks? Yeah, I think they call those blocks. It's 16 by 16 pixel blocks, and then in that there's 8 by 8 pixel tiles. So 4 tiles make up a block, and then what is it? 8 tiles make. Oh, sorry, 8 blocks make up a 8 by 8 blocks make up a chunk. This is called a chunk. So we're operating at the block level. So we're taking a block and saying that the collision, is that right? No, it must not be right, because, oh no, it is right, because this is 16 by 16 pixels, isn't it? I think it is. I think it's 16 by 16. Yeah, so each one of those blocks has a 16 by 16 pixel collision. So each one of these blocks here represents one of these. So see how this one's kind of slightly going down, probably. It would correspond to one that's slightly going down. Although these can be flipped as well. So it could be corresponding to one of these which is slightly going up, but then they flip it. So it is possible to flip it down. So yes, so that's what we're looking at. So that's a collision thing, and I'm thinking that really the collision is probably more accurate. Like if we got the collision index, so this says like the collision index is basically, so here it would say this block's collision index is OC. It would say OC, but with a couple of flags to say whether it's flipped or not. But it could say OC, and so then you'd look at that, and that would be the part over here. So I'm thinking like if it said OC, then what we could also index, like I'm just thinking that if the collision index is OC, then why not reuse that collision index for the angle data? Like this collision says what the angle is. I mean, the image might not say what the angle is because, you know, it's got, you know, grass and stuff on it. So, but this thing does, because it says, you know, you can collide with this pixel, you can collide with this pixel, and you can collide with all these pixels. So it's kind of, it seems like to me that the collision data has the idea of an angle. because you're colliding with certain pixels in it, and so it's kind of got an angle kind of built into it. So what I would think would be a sensible thing to do would be to use this index that we're using here to index into the collision data, to also index into the curve data. I think that would be a sensible thing. I don't think that's what's happening though. We are reusing, is it collision curve map? So we are using, oh, we are using that, pointer to collision data. Okay, we are using exactly that. Oh, curve map is collision curve map. Because this is the collision data, isn't it? Is that right? That's collision data. It is. So that's exactly what we're doing. Cool. Okay, so I already have the collision index loaded. Cool. Okay. Okay, that's making some sense. So we've got the collision index. And so then see how here I'm re-indexing the collision blocks. And what we could do is re-index the re-index the curves. Something like that. There we go. Okay, let me run this. I'm just thinking that we have to re-index it, so then we can index it by the block. So index it by the block ID. Yeah. So the re-indexing will go off and read each, like it will kind of like rearrange everything. So basically, I've got this big array of block IDs to the angle data. So block ID whatever here, like so block ID this index has 240 as the angle. If we scroll up, we should hopefully see more than 255. There is a lot of 255s around. But yeah, so when I say like, hey, I'm standing on this block, I should be able to index into this and say get out the exact angle. So I think that's right. Yeah, I think that's good. So yeah, so then we do collide with level, and I've got this re-index collision blocks. So where do I do collide with level? Up here. So I've got this collision blocks. I get it out. There we go. Okay, so that's the collision block. And that's right, I update the player's position, don't I, with that? So what I can do is I'll also pass in, this is all super dodgy, needs to be fixed up, like everything else I've written so far. But we'll have re-indexed curves, access by the block index. And then I'll set the player's angle to angle. Cool. And down here I'll need to pass in the re-indexed curves. So one day I will get around to cleaning this stuff up instead of making more and more of a mess. Okay, hopefully this compiles and we can see, I mean, actually what we should be doing is printing out, after every frame, print out the, what am I using for graphics? I'm using SDL2. Okay, so, I don't know what's happening there, so let's print out the, player angle. Give that a run. using just SDL2 for the graphics and input and everything. I've been kind of I've been careful to only use to use texture graphics as much as possible. Okay, that's interesting. So we're standing flat, 255. And notice when I go up on this hill, 248. And then on 255, I'm flat, 248. So there's something happening there. I mean, 248, it looks like 248 on both sides though. Like, one of them seems like we're going down slightly and one seems like we're going up slightly. So I don't know why they're both 248. So it's 248 going up. So I feel like going down, it should be not 248. So I don't get that part. But, you know, like there is, like, I mean, this angle data is doing something, like, so you notice how when I'm going up, it's kind of, I don't know, it's doing something. So 216, 212. So it means something, I just don't know what. I don't know why when you're going up and when you're going down, there's 248. Actually, what I'm thinking is that what I've done is I've taken the collision indexes, right? I've used the collision index to index into the curves, right? I'm thinking that I'm using the collision index to index into the curves. I'm thinking that actually, because the collision index has got more data than just the index. The collision index also has the idea of what do you call it? Has the idea of flipping. So this collision index has got the idea of horizontal flipping, I think, and vertical, horizontal and vertical flipping. And so that curve that I'm indexing into the curves with the collision index, which has got horizontal and vertical flipping in it, and that's not being taken into consideration when I'm indexing into the curves. So that's the problem there. I'm certain that's the problem there. So the collision index, if we printed out all the collision indexes, if we printed all these out, there'd be more than just 0 to 255. Like, there'd be more than that. There'd be, because it also includes the flag of horizontal flip. I think I've got that in here somewhere. So here we go. I load the collision blocks. I think. So like I was saying before is that what I was trying to say before is that with SDL2 I've been really careful to make sure I have I use textures as much as possible instead of surfaces. Surfaces are software rendered. Like SDL2's got this idea of like surfaces versus textures. Surfaces are software rendered and textures are hardware rendered. They're kept in hardware RAM and you kind of like just render them really quickly. And so I've kind of got the idea of I've made sure that in places where I have to use basically the surface because I'm using something, I'm doing something software. I'm basically using software to render a surface. Then I convert it over to a texture, and then I've got like a static like texture that you can't really modify, but you can render really quickly. So basically everything is hardware accelerated is the point there. Pretty much everything. Whenever I move Sonic around, or like basically everything that you see is hardware rendered. There's a couple of points during loading where things aren't hardware. Like, I mean, basically because I have to load things up, I have to generate the textures, and so at that point it's software. Some parts are software manipulated. Okay, so these are the collision bitmaps that I generate, and then I convert them over to a texture somewhere. So load collision texture. So here, yeah, this is where I create a texture from it. And then where do I flip it? Oh, okay. What's that? So what is it? It's blocks can be flipped when they go into a chunk. So is that what happens? So I'm trying to remember where things get flipped. Because I know that there's the idea of horizontal and vertical flipping, but I'm thinking maybe that's not at this case. Yeah, I don't think it's at this part. Yeah, I don't think, so I don't think we actually flip it when we load up the collision data. I think we actually flip it when we combine them into a chunk. When we take all these blocks and put them into chunks, when you see collision data that's upside down, it's actually because the chunk has said, take that block and flip it. So I think when we are indexing in by the collision index, maybe that is fine. I'm going to print out all the collision indexes. Indices. We'll see what happens. I don't even know how many collision indices there are. Okay, so they all are just bytes. So yeah, it is actually referencing the right, I probably should just look at the type of what a collision index is. I don't have it here, but here we go, load collision index. So load collision index has the type, what? Whoops, wrong thing. Yeah, word 8. So it is 256. Different values for that. So curves, so it should be able to access curves. Yeah, okay. So reindex curve. So that's fine. That's fine. What I probably have to do, yeah, okay. What I probably have to do is, it must be up here. I must already have it here. Yeah, I reckon this is what's going on. So chunk block. Here we go. This is, I think, what's happening. So chunk block, flip X and flip Y. There we go. So we're not actually using it when we're doing collision. So that's interesting, right? So that's interesting. When we do collision, I'm not actually taking into consideration whether the thing is being flipped. Oh, you know what? That explains a lot of things. And I've been complaining about this bug for a long time. I'll show it to you, and I'll explain what's happening now, because everything's just come together. This will make things a lot better when I fix this bug. Okay, so what I was saying, right, is when I go up here, notice how it's 248, so it's like kind of saying, okay, cool, we're going up. Got to the top, 255, okay. Then we come in here, and it's like 248 again. Why? What? That's weird. I don't know if anyone just noticed that, but you could actually see the bug. Notice how when I go across, keep going across, notice I fall down, and then when I'm going across, notice how I'm going up slightly. Okay, ignore that for now. Now let's go across. Now watch this. Notice how I'm jumping up each time. Notice how I'm jumping up. So I'm bouncing around. Whereas on the other side, if I walk up here, right, if I walk over here, smooth. Super smooth. Super smooth that side. But then on this side, I'm bumping up and down. It's because all of these collision things they're meant to be flipped, right? So it's meant to kind of like, it's meant to collide like that. It's meant to like go downward. It's meant to be downward hill. But I'm not actually flipping these when I do collision. I'm not actually flipping the X and the Y when I do collision. So when these are all actually, these do have the flip flag set, and I'm just not taking that into consideration. So when I'm going down, I'm not actually flipping the collision, so they're actually all pointing up. So I've kind of like got like a really jagged collision map here. So that's really the problem. So I just need to take into consideration flip X and flip Y here, and then that also would explain the angle. I also need to flip the angle based on this flip X and flip Y. So there we go. Things are starting to make more sense. Flip X and flip Y I need to take into consideration. So, so here we go, we'll have heights. So I need to manipulate these heights in some way. So if flip X, then reverse else ID of that. Can I do that? Oh no, because I need to do it on the heights. Go with that for now. Oh, I can't reverse a bounded array. That's annoying. Can't reverse a bounded array. What I can change instead is annoying but totally reasonable. Yeah, maybe. Yeah. I don't know. I feel like I should be able to make like I should be able to write like some sort of you know, comet lens optical thing that represents the idea of like some sort of traversal or something, that, or an index traversal that can do something like that. But I think I could do something like that. But anyway, what I'll do instead is here I'll have some special stuff. So I'll say let X equals if flip X then 16 or OX F, actually I think it is, take pixel X else pixel X. Let's look at that, maybe. Hopefully we'll have a smooth, it'll be smooth. Hopefully it'll be smooth. We'll see. There we go, it is smooth. It's definitely smooth. Oh, that's cool. That is good. It's good that I fixed that bug that's been annoying the crap out of me. There we go. Whoops. Too fast. I really need to fix using lists anywhere. Really need to use lists. Need to stop using lists. So here we go. That's cool. That's really cool though. It's really cool that we can actually smoothly go down. We can go up and we can go down. Cool. I'm happy with that. I'm really happy with that. Okay. Alright. Yes, we're actually getting somewhere. We're getting somewhere. Blast processing, exactly. Blast processing. Okay. And now angle. What do we do with angle to flip it? I think there is some logic in the ROM that we saw about flipping it. Get angle from the map. X flipping. Here we go. Let's look at the C code. Let's see if the C code is more understandable there. Oh, what's happening? Oh, no. That's not the C code I want. What do they call it? They call it bat, didn't they? Bat. Here we go. So if... I'm guessing this corresponds to the X flipping and this corresponds to the Y flipping. I'm just taking a guess. Yeah, it looks like it. It looks like it. Okay, and that corresponds to the X flipping. So basically what they do is they just, what do they do? I don't know what's D1 though. Move the X position into D1. Then they, whoa, I don't know what's going on with D1. But they do just negate A4. So it looks, what's the negative word 8? I don't think we've got that idea. What's a negative char in C? I guess you got signed characters in C, that's right, so it just negates the angle. It just negates the angle. Because I think A4 is a char, is that right? Minus would flip the MSB. So if we have 200 and, what do we see, 230, no, 6 or something like that. Let's say that's a word 8. There is, data.bits has, what's it got? It's got the, it does have negate, but I think that wouldn't do anything for a word 8, so maybe our word 8, like, if we complemented 236 as a word 8, we would just get something not very useful, get 19. But is that okay, actually? That might actually be okay for an angle, wouldn't it? Would it be okay for an angle? $19 would be the flipped. Be the flip version? There might be. What would be a horizontal flip then? Oh, okay, that's why they're doing the take 40 on that. So yeah, maybe that is fine. Maybe complement would work. Maybe complement is right. Yeah, thanks for that. I think you might be right with. I mean, yeah. I think that's close. Yeah. Thanks, Scott, for the follow. Okay, so if we come up here, 7, and down. Oh, whoops! I'm always complementing it. I want to say, whoops. If flip X, then complement else ID. Whoops. That. Okay, try that. So let's try this. Flipping Y is a little bit more complicated, but we can do that later. It's not that much more complicated. It looks like it's just negating OX40. So we go going up, going down. Cool. This actually corresponds, I think, pretty close to what we saw in the game, because I do remember seeing 0 every so often, and I was wondering what the difference between 255 and 0 was. I was wondering what that difference was, and I thought maybe 255 was maybe like a special marker to say that there wasn't any rotation, but now that I see 0 here, what it actually means is that we're complementing the 255. So 255 does mean, you know, that there is no rotation, but we're complementing it because we're saying certain things are flipped. We're saying certain blocks are flipped. And so even though they're flat, they're still flipped because visually they're flipped. Although it's at the collision level, so I don't know why they would flip the collision if you're flat. But anyway, maybe not quite flat, I don't know. But yeah, so 0 is, I think, meaning just that is flipped, just that is a flipped collision thing. So that now that we see 0 there, it actually makes sense to me in this case, because we're actually flipping it. We're complementing it. So yeah, so I think seeing 15 was pretty common as well when you're kind of going upwards. So I think we've actually got the right angle data. I think that's actually pretty close. So it's looking pretty good. Yeah, it's looking pretty good. Okay, so what I will do is, I guess what I'll do is I'll try and get Sonic to update his, well, I mean, the thing is I don't even have any really, any animation around, around Sonic walking or anything at the moment, so it doesn't, I could rotate Sonic, but it's basically, yeah, I've got no Y-axis at the moment. Like, there's a lot of things I haven't really done about Y. You can see that it's completely stuffed up with the collision of Y, so that's something that I really have to do. I was just saying that I was trying to say that I want to make it so that Sonic actually rotates as he goes around something, which means like basically transitioning his animation to go to the right. Gonna do the Y-axis before I end the stream. I don't know. I mean, there's just a lot to do around the Y-axis, so I don't know if I'll actually get around to that. We can have a quick go at some of it. I just don't think I'll be able to finish it off. I think that there's a lot of stuff around like colliding with the Y-axis that I haven't done. Like you can see here, I've got collision with the X-axis. That's pretty, that's pretty straightforward. But to collide with the Y-axis, I don't really have. Also, there's some idea of like solidity, so things can be solid from the top and not from the bottom. So notice here when I jump, notice how when I hit this bottom part here, I kind of teleport up. This would actually be not solid from the bottom. It would be not solid. So it's only solid if you come from the top. And I don't have any idea. Like, I haven't implemented that. I haven't even got the start of anything like that. So I haven't... I don't think I've even got the data in there which says that this is not solid from below. But ideally I'd have that so that when you jump, you can jump and not actually collide with that. And so see how like I'm kind of like... my collision logic is always like, if you collide with something, just put you at the top of it. Just, keep moving you upwards until you're not colliding anymore. Ideally, what I'd have is, like, even under this logic, I could say, be not solid from the bottom, so when I jump, I don't actually, like, get teleported. I can jump and still just kind of, like, land on the thing when I come back down. Thank you for the follow. So anyway, there's that. I'll have a go at, I'll do some more of the Y-axis. Yeah, what I wanted to do was work on getting Sonic rotated, but that would be me transitioning Sonic's frames based on like transitioning his animations based on the level, which I haven't done. All I've got is Sonic sitting in the idle animation at the moment, so I've got nothing around moving in between different animations. And one of the tricky things is that with Sonic's walking animation is when you move around and you play his walking animation is actually played at a different speed depending on how fast you're going. So if I'm going at this speed right here, Sonic's walking animation is not that fast. Whereas if I keep going forward, eventually his walking animation goes faster, and eventually he transitions into another animation. He kind of goes into his running animation. So there's a little bit of like actual logic around like some of these animations, like this idle animation. I can just say play that animation, play the idle animation, and you can see it's just playing at the moment. There's no special logic in there to say play this animation. It's really just me reading from the ROM file and saying play that part of the animation, and the logic, there's kind of like an animation script, and it just plays. Whereas with the walking animation, there's a little bit of logic involved. It's actually like got some custom logic for walking. So as much as I want to do the do the angles and that, I think I'll have to actually start implementing the walking animation to be able to get to that point. So I think I'll leave that. What I will do is I'll have a little bit of a go on the height though. Actually, I'll commit what I've got because I think what I've got is useful. I think this is one thing about VS Code that if I start using VS Code, I think I'll miss this part of Emacs, the Magit integration. Yeah, so we don't use the Y information there. We do use it down. Whoops. We do use it down here. So I need to say that. What do I need to say? So I need to say pixel Y. So instead of like, I think I need to basically do this. I think I basically need to do that. Something like that. That was a pixel Y. There you go. Flip is actually a thing, isn't it? What should I call that? Flip is actually a useful function in Haskell. Okay, we'll go with that for now. Okay, so I don't know. That should do something. I don't know where I can really test that, but that should do something. So that should be something for the y-axis. So basically, if we're flipping the collision block, I don't know. If we're flipping the collision block, then I will collide a different part of it now. Like before, I was only treating it so that if you flip the collision block, then I don't think you'll really be able to notice what I've done just there. I don't think that'll really change anything around what we can see so far. So I don't think that was the most useful part of this. Yeah, I don't think we've got to notice anywhere that we're doing anything with that. Okay, so there's that. Where else could we use the Y? I mean, really what we need to do is update the collision, the actual collision stuff, so that you can kind of collide with so collision actually happens. So collision happens and not like what I'm doing is just say that if you collide, you just keep teleporting up to a point where you're not colliding anymore. I need to do better than that. Like that's just you know, my testing for the collision, so just testing that collision works at all. I need to actually make that collision is actually collision instead of collision is teleportation. So that's really, I guess, the next thing that I need to work on. I've got the curve information, which is really cool. I'm really happy that we finally got the curve information in. We are only, like, I didn't really go all the way to, like, how many degrees it is. I don't think we actually need that at this point. I don't think we actually need the degrees. I was actually thinking that we need the degrees to be able to rotate the sprite, but turns out the sprite has got all the information in it to do the rotation. So thanks everyone for pointing that out. That's really useful. Yes, so now we've got the angle information. I guess what we should do, right, based on that angle information, what we can do is jump differently. That's one thing that we could do. So jump should take into consideration here we go. So we have this angle here. So that's already something that yes, that we didn't translate over. So actually let's have a quick look at jump. Whoops. Sonic jump. So here we go. We use the angle to calculate, and then we calculate the sine of that angle. So we get out the angle, we take off OX40 for some reason, calculate the sine of that. D1 is, I can't remember, calc sine does two things. It calculates the sine and the cosine, so I don't know what D1 is, but it does something with that. I'm not sure what D2 is. What's D2? Oh, it's just like yeah, it's the jump speed. Okay, so it multiplies the jump speed by the cosine maybe, or the sine, I can't remember whichever one it gets out. Yes, and then adds that onto the x velocity. Adds it onto the x velocity, but what we have so far is we are we're adding onto the y velocity here. So sine. Okay, yeah. So x needs to be cosine. That's it's the cosine here that it uses. So multiplies the jump speed by the cosine to calculate the y speed. I mean the x speed, sorry. Okay. But what we could do is let's use this angle actually. Use player angle. Okay, and then oh, that's right. So we need to use this calc sine. So let's write calc sine real quick. Let's write calc sine. We've got enough time. Let's write calc sine. I'll make my own module for it because it's. I know it's just a weird thing. This sine because it's. I mean, I guess it's not that weird. We just can't use the sin function from Haskell because it's. I don't know, it's just got Sonic's included its own sine wave. So here you go. Here's the sine data. So it's got all of this sine data just kind of built into it. Calc sine. Unit for now. Really what it should be is word 8. Word 8 I think is what we're going to be calculating out. Is that right? Calc sine, word 8, word 8. No, because it's actually word 16, isn't it? 2 word 16s. Okay, and this will need sine data. Yeah, I hope you'll be able to switch between the two sine functions at some point to see the difference in game. 100%, that would be so cool. It would be really, really cool to be able to say, you know, instead of using, you know, instead of using Sonic's sine function, let's, you know, put in Haskell's sine function. No, I think that would be super, super cool, and we should be able to. We should be able to get enough abstraction to be able to do that. I think that would be super, super, super cool. Okay. So calc sine. So word 8. So it's a word 8 indexed of word 32s. Oh, hang on. Hang on, what's happening here? So it calculates, so it gets... So we got the sine data. Get out D1. So it's D0. Looks like it's exactly hard-coded sine values. Is exactly what it is. 100%. That's exactly what it is. Yeah. If we look at the Sonic 2 disassembly, and we go to sine wave, there you go. This is a sine wave in. That's the sine wave data. That's 100% what it is. Exactly a table of a sine wave. Yeah. They've pre-calculated the sine wave. I guess they were referencing this data a lot, and so instead of calculating it on the fly, it makes sense to hard code it all. At least it's fast, exactly. Gotta go fast. Okay. So that's the sine data. I think I've got in the right format. What's interesting to me here is that what is D1 and D0? It's getting out the... So D0 coming in is the like kind of like the offset to calculate for the sine wave 4. I was thinking it was a word 32, but it must be word 16s. Yeah, it's a bit, yeah, there's a bit miles there, yeah. Oh, I see, because there's 320 values, right? I see what's going on, right? So there's 300, I was a bit confused there, but there's 320 values, and that's cool, 320 values, but, and they're offset by OX40, which is 128, right? 128 is no, it's 64, so it's offset by 64, so basically you get 64 of these values, and then that's where the other one starts. So I can't remember which one's sine and which one's... Let's look at this. Calc sine. So D0 is the sine and D1 is the cosine. So cos is calculated by... Cos is D1. So cos is calculated by shifting it over 64 elements, 64 items, whereas the sine starts at 0. Cosine starts at 64, sine starts at 0. So that makes some sense. Now, what I have is 320 values, and word 8 represents 2 to the power 8, which is 256. So I can't keep it in there. I also don't want to keep it in 2 to the power 16, because that's a lot bigger, but I think I will for now, just because it's got enough information in it. But it shouldn't be a bounded array of word 16 by word 16. That's too big. But anyway, we'll pretend like that's not going to be a problem for us. But that'll be a word 8 that you pass in. And so then what we can do is access the array with from integral w, and then access the array with from integral w plus 40. There we go, that's the calc sine function. So that's calc sine. Cool. So in player, when we jump, we'll also have to put on a constraint that we have monad state. Actually, monad, I don't know. I don't know, something like that. Something like that. What's wrong with that? You know what I should do is has sign. That's really what I should do. And say word 8 That's really what I should do. Because then I have got the I like that. This is exactly what you were asking for, kind mind. Kind mind. This is exactly what you're looking for. Because now we've got calc sign, so we can just say has sign as a constraint, has sign. Oh, I need to export it. Okay, getting close up. There we go. Now we've got the angle out, and so now I should be able to say sine. Awesome. Check out that. Expected an int 32. Oh, whoops. Oh, right. Yes. Sign is first of that. Probably have a better data structure than just a tuple there, but anyway. Cool. Okay, let's so we should have a problem in main, because yes, main says jump wanted a has sign. We don't have a has sign for whatever we're using. What are we using? Reader. This one has could keep doing this. Is there an easier way to do this? Yeah, this would be an easy way. I can't do that. Can't do that. I think I'm going the right direction before. That's kind of annoying though. I don't really like that. Don't really like this. Yeah, I don't like it. What can I do instead? Yeah. Don't like it, but I think for now, I guess. Yeah, I guess I can do that. Yeah, but I don't want to do that either, actually. Yeah, I kind of want to make like a whole main app that actually specifies which sign to use and that. Maybe I should go with this for now. Don't like it, but I don't like it. I'm gonna do something not as good as what I wanted. Not as good as what we wanted, but I'm gonna go with this for now. Yeah, make it work is always better. Yeah, exactly. I don't like this anywhere near as much as what I was going with, but it's just a bit more work to do what I wanted. It is possible. It's definitely possible what I wanted to do. It's definitely possible. It's a bit more work. So I'm thinking, should I do this or should I just do something? I don't know. Should I just go with something a bit more interesting or? I'll just do this. It's not good, but do I even need to do that? I'll just do what I've been doing elsewhere, and then we'll change it over to do something better later on. There's probably more places than people rarely make it past step 1. They rarely make it work. Yeah, that's true. It is true. Thank you for the follow. Sign data. There we go. We'll go with that for now. It's gross, but it'll work. It'll just be easy for me to work with. Because now I've got my game. And I can add on my sign data. It's not great, but it'll work. Hey, Prof, how's it going? Actually, that's the ROM. Do you deal with a lot of sloppy code at work, Fresh? With Marketplace, it's actually written really, really well. Marketplace is like it's the main thing I work on, and it's actually really, like it's Scala code, but it's actually done like, I mean, the sloppiness is all from the Scala side. It's not because we've really like there are some mistakes that's been made. I mean, it's a 10-year-old code base, so there's some mistakes that have been made. It's not really because of the code. It's more of like the data modeling and like the like some of the implications from how people have designed things. It's not really implications from just someone used a .get on an option here or something. Like there's none of that sort of stuff. It's all like total functional programming. Or as close as you can reasonably get with Scala, which is, you know, there's variations there. But yes, the code is actually really, really well written considering the constraints that we've got, which is Scala and like not great data model and things like that. So yeah, so I mean, there's some problems with the code that I work on, but it's not really with the code itself. It's more of like the design of certain systems and things. I'm actually really lucky to work on the project I work on. It's very, very well done. Oh, okay, I've got a lens for the sign data. Annoying. Okay, that's fine. Guess I don't really actually ever want to update the sign data though. It's really just it really is just a getter. Yeah, it's just a getter. Why specify this as a lens when it's not actually a lens? Well, it is a lens, but it's just. problem there? Is it asks? Yeah, it's asks, isn't it? What's the problem with this thing here? Oh right, I had what I wanted before was actually right. Okay. Here we go. Okay. Okay. Got something useful there. Okay. So signed data is actually just a function now from our game. To a value. So G is our game. I want to access the ROM part. So now we got back a ROM. And then I've got this offset thing, which I want to get out. What's the offset of the signed data? Here we go. 33 CE. So 33 CE plus, how many values was there? There was 320, wasn't there? So 350E, 350E. So I think that's right. So now I should be able to say load. Should be able to say, oh, awesome, there's even slice ROM. Slice ROM at sign data. Offsets or sign. Did I have sign data in here? Oh yeah. I don't want to call it get sign data, but it's kind of what it is. What I should say is offsets dot. How about that? Cool, getting there. 76. So slice ROM gets me back a byte string. Then I want to say list array fill 0 that. Sorry, this is probably really boring. Okay, so list array fill is giving me what? Oh, I have to unpack it, don't I? bs.unpack that. Oh, that's right, because I need to make a bounded array of word 16. Do I do that somewhere else? I must do it somewhere else. I must do it somewhere else. I think what I'd use is, yeah, this, here we go. No, I'll do something like that, don't I? Alright, let's try this again. So, slice ROM. So collect halves. Collect halves is something I wrote, which is like, it will take, there's a couple of ways to instantiate collect halves. Let me see if I can do that. Dot halves. So for example, if I've got 0, which is a word 8, and 1, which is a word 8. So imagine if I've got that as a list. So this is something I wrote. So I don't know. I'm kind of conflicted on it. So if I've got that, right, then I should say be able to collect halves on that. Oh, it's a lens though, so I need to say collect halves. And what it's done is it's kind of combined these two into a word 16. So if I look at the type of that, it's a word 16, but also I should be able to say it like that actually. That'll make more obvious what's happening. So you can see here that I've gotten a word 8, and I've got a word 8 here, and I've kind of combined them together, 2 word 8s into 1 word 16. And so you can have kind of like a list of word 8, so you can have a list of bytes basically. So 0, 1, 2, 3, 4, 5, for example, and see how it's actually just kind of collecting these 2 bytes. Every 2 bytes kind of gets put into a word 16 now. So I've got every 2 word 8s gets combined into a 1 word 16. So that's something I wrote, uses functional dependencies and that. I tried having a go at translating over to type families, and I don't really like it that much. I don't like the type family version that much, but I should probably publish a blog post describing the differences between what I see, basically the differences between functional dependencies and type families for my case there. Come on, we're getting somewhere. 79. List of word 16 with word 16. List of word 16 to word 16. So slice ROM is given back as an M of byte string. Oh, okay. What I need to do is actually supply the G, don't I? So slice ROM. Is that better? Well, then I don't even need to fmap it, do I? There we go. There we go. And there we go. We've got something there. Cool. Awesome. Awesome. So now with my main, I need to also supply the sign data. Oh, that's annoying. So that happens before the ROM. Oh, that's really annoying. Okay, different idea. Different idea. I don't want to do it at the level of the game. I don't want to do it there. I don't want to do it there. I actually want to have sign basically extract out the sign from the game ROM. So we've already got this like idea of has ROM. So basically I want to say like has ROM. I basically want to do that down here. Basically that, something like that. But yes, what can I do with that? Kind of want to like translate. I've got like a reader that says it has a ROM. I want to translate into a reader that says it has sign data. So basically want to translate it over to something that can kind of calculate the sign data. So there is it locally or something in Lens? Oh, okay. That's not ideal. Okay. I don't want to use this. Here we go. We've got some documentation. So zoom. Oh, that's internal. I don't want internal. Acts like local. We can change the type of the environment. I don't really, yeah. I think we just want local, don't we? Just local. Probably shouldn't have equal or odd for that thing, but whatever. Okay, and then under main, we'll do it there. Actually, I guess I can just do. Is that right? What's wrong with that? Calc science not in scope? Yes, it is. Should be. Yeah. Okay, it's just out of date. That's something I don't like about Dante. It gets out of date pretty easily if you're changing many modules around, which I always do. Okay, and yes, main has signed data, so I actually need to load it up. So signed data will be, what was that collect half? Where did I have that collect halves thing? I don't think I actually wrote it down anywhere, did I? Yeah, I didn't write it down anywhere. Oh, I did. I started writing it in here, but I don't need it in here. Don't need that. Don't need that. Get rid of the stuff I didn't need. All right, back to where we started, and it's now signed data prime equals. Actually, no, it's slice from signed data. Yes, and then we that. That. Is that right? Yes. Sorry, I've been screwing around a lot with this, and I think we've finally gotten somewhere. And what did I have to do with that? I do list array fill. What's wrong with that? Why doesn't it like that? Okay. Yeah, alright. Okay, that's easy to fix. We will actually make a return sign data. There we go. Okay, alright. Okay. It's just ambiguous because it's like trying to create an array and it's trying to infer, you know, what constraint and that. I mean, it makes a lot of sense. So what I just really need here is just need to say that this is a sign data. I need to import that now. Okay. I need to come up with like a naming convention for the offsets or something. It's just so that it stops conflicting. I don't think I exported it over here, did I? Yeah, I didn't. Alright. Yes. We've got something, finally. It only took me forever. Okay, okay, so now jump. Uses the player's angle to get out the sine wave. Hopefully, maybe, that'll be right. And what I should really do is, I mean, I should also add x on, right? I should also calculate what x is. What was the problem with me doing it up here? What was the problem with me doing that? Was there a problem with me doing that? I don't think so. Okay. Okay. Will that do what I want? Let's run it and see. Let's see what this does. Okay. Actually, there was some more logic in jump, wasn't there? Jump also did, that's some speed, exactly. I also did this, yeah, like I was adding things on. Let me go back to the C version and we'll double check. Oops. Sonic jump. Okay, so it gets out. So this, I'm guessing this is X. So what to do? If d0, so it multiplies it by the, multiplies the cosine by the speed. If it's less than 0, then it does something. So maybe that is part of our problem. Maybe the cosine is less. Although we're getting out word 16, so it's never less than, it's negative, never negative. Maybe that's the problem. It's never negative because we're just treating it as word 16. So if you look at the data, you know, it's just 0 to, I mean, yeah, it's just 0 and it goes up. Oh, but this FF, oh, so it is negative. So these are not word, hang on. So these are negatives, right? The FF, yeah, those are negatives. So it actually, okay, so these are not, what I've been treating the sign data as is word 16s, but it's actually int 16s, isn't it? I think those are int 16s. Whoops. Okay, so I've got those collect halves, which is word 16. Okay, yeah. So in main, I need to okay. So now I've got int 16s now. So we do actually have negatives. So I don't know if that'll, things will still probably look super broken, but we'll have a look. I think theoretically, if we're standing on flat land, it should be the same. If we're staying on the flat part of the land, it should be exactly the same. No, because we're moving forward. Why are we moving forward? Did I flip it around? I don't think I did. No, I didn't, did I? Because D1, if we look at calc sign up here, calc sign, D1, that's the cos, and D0 is the sine. D1 is cos, oh, it's 255 times sine, but anyway. I don't think that matters. I think that's what we're using anyway. Okay, so you know what I should do is trace sine and cosine. I just want to see what this is, just to make sure that they align up as actually like sine and cosine. So it did there. 0 to 55. Okay, I think that's fine. And then on this slight angle here, let's see what it is there. And what was it? 0 and 251. That doesn't seem quite right, but let's go on more of an angle to see. Let's go on a more steep angle and we'll jump. We'll come up here. What was that? 0 and 212. So it's always 0. Sine's always 0, it seems. That doesn't seem right. One thing we do have to, I don't think I did, was yeah. Is that right? Yeah, I think that's right. Maybe that was a problem. It probably was related to that. Was it? Oh no, but the angle can only be, because the angle is a word 8. Yeah, that was not a problem. That was definitely not a problem, because angle can only be a word 8. So, I mean, that is something they did in the actual implementation of calcsign, but it's not something we have to do for us, because we know that it's a byte. So anyway, jump here. Okay. So what's the problem when it's like when it's a low number like 7, for example, it's right, but when it's 248 or something, it's 0. Why is it coming out of 0? So it should come out as 19. Is it not reading out the... Is it not reading out the whole thing? What I'll do is I'll print out the sign data. Wouldn't it be faster to write C to Haskell compiler supporting only Sonic C code? Then we'd have like C in Haskell, which is not what we want. I'm trying to write abstracted Haskell code from the C or from the assembly, so I don't think so. What do I want to do to be able to print this out nicely? I'll just print out the first 255 of them. I don't really want to use the Sonic C code anyway, because that was someone that wrote the Sonic C code. It's not actually, like, Sonic was not written in C, so it's not actually the real Sonic code. So you'd actually have to convert Motorola 68,000 K assembly, sorry, 68,000 assembly to to Haskell, which you could do, but I don't think would be very nice to do. Okay, so 255. Actually, let me just make sure. Calc sign. Yeah, we are dealing with words. Okay, we are dealing with words. Okay. 255, 6. Okay, so we got 0, 6, 12, 18, 25, 31, so on. Until we get OFF. Where's the OFFs coming in? Yeah, so then we get those, then it goes down to, here we go. 0, 0, 0, 0, 0, 0. Why all these zeros? Is that right? It seems to go up to that, which I reckon would correspond to that. I'm guessing. Okay, that's index 9F. To me, it looks like something I'm doing something that could be automated. I don't think that's true. Some of it could definitely be automated. I'd love to see the automation though. If you can automate me away, please do. Please automate this tedious stuff away, please. I would love for it to be automated completely. What's going on here? At 9F, I've got EE. Okay, so that's FF50 there. I really don't understand what's happening here. So we've got 0. I want to see the hex numbers. I want to see the hex representations of these numbers. Okay, so let's see how they correspond to what I have. So FF50, 55. Is it going backwards? Why is it going backwards? 55. FF59. Yeah, so it's going backwards. What? What's supposed to empty string for show hex? Like, so like, I don't know if you know about the shows function, show s. But if we look at shows is like string to string, and so it is possible for you to implement instead of when you go to implement show, most people will implement the show function, but it is possible for you to implement basically everything in terms of show s. So you basically got this type of thing, shows prec. So it is possible for you to implement everything in terms of show s. So I think when you have, was it show hex from numeric? When you have this, it's actually, yeah, there you go, show s. It's exactly for writing a show s. So like the idea is that you give it like a string, like kind of like basically a prefix or something. So if I say 10, I could also say test. Well, it's a suffix actually, so there you go. So this is the rest of the thing to print out. It's basically, if you want to look up more about it, look up show s in Haskell. That's the reason why I have to put the empty string at the end. But it's interesting because this thing is backwards. I am somehow reading this thing backwards. What? Oh, actually, let's look at my offsets. 3 CE. No, though I thought maybe I had this backwards, but no, I don't. That's fine. That's in the right. It's ascending. Does my collect halves function do it traverse backwards somehow? The use case is when you want to compose like shows together. If you look up what show s is used for, it's basically for composing together show instances. You have to go have a look at what show s. I think there's some documentation somewhere what show s is used for. It's basically for composing together show instances. So, I mean, we're not composing anything together, that's why I'm giving it the empty string, but there are cases where you want to kind of compose them together, and so you use show s. I'm just going to have a quick look at my halves library. I'm confused by this, so I'm going to go even one step before this. I'm going to print out the slicing of the ROM, and we'll just keep doing this. We'll just keep building up. Just making sure that the data is what we expect it to be at each point. So, print out the data. Let's run that. Okay, this is also saying it's efficiency. There you go. So I know it, yeah, okay, so it does make a difference list. I thought also, I think this is what I'm thinking of, the shows prac, so it's more of the, I guess though it is just an efficiency calculation actually. It uses it's a difference list. So I thought it allowed to like, yeah, operator precedence. So use show s to get operator precedence. Basically, when you're composing together show instances, but it's actually for efficiency. That's why I use it to compose together. It's not actually more capable. It seems like maybe allows handling of operator. I mean, shows prec does allow you to do operator precedence. So maybe it does. Maybe it does add in behavior, but it looks like the main thing people are pointing out is that it's because it's a difference list, that's more efficient at concatenation. So why is this not working? There we go. It's running now. Okay, so that's the data. Okay, and then let's print it out as a list of bytes. Show S is all about being efficient. Same applies to show hex. Okay. So that looks right, maybe? So those are all the bytes. Actually, is that not right? Can I plot it? Yeah, it would be ideal if I could plot it, wouldn't it? 0, 0, 0, 6, that's right. 0, 12, that's right. 0, 8, oh, 0, 18, yeah, that's right. 0, 25, yeah, so that's all good. Then we get 25, 120. Did I add the wrong number on? 27F. 27F. So I was meant to add on 280. And what did I add on to the offsets? Okay. Let's try again. I think I just had the wrong offset there. I mean, I calculated it myself. So I must have screwed up there somehow. Okay. There we go. 0255 to 0255, 0255. Yes. Okay, now I've got the right data. That is the right data being loaded in. Okay. Now let's go back to my main. Let's just try the original thing I wrote by commenting out the print. Actually, I didn't even have to change anything there because I'm already printing out the angles on that when I jump. Alright, so hopefully now the sign data won't always be weird. Okay. I don't know why it's -6 when I'm standing still. I don't know why that's -6. 43. Doesn't quite look right. I mean, it definitely doesn't behave right, but it doesn't look right either. Why does it take so long to load the level? Just because I'm using inefficient data structures. What do those values represent? Coefficients? No, those represent the sign and the cosine. So the first one, sorry, the first one is the angle. So the angle out of, like, so imagine degrees, but instead of up to 360, imagine it's on a 256 scale, so 0 to 255. Second number is the sine. Third number is the cosine, and don't imagine sine as, you know, as a real number between -1 and 1. Imagine it as -255 to +255. Numbers just seem weird. They just seem weird. Negative. Like, I can't, like, well, you would expect sine and cosine to add up to 1, wouldn't you? Well, sorry, to not add up to 1, but to be offset by, what is it, 180 degrees? 90 degrees. And that's not quite true there, right? Add scaling to your debug values to get more intuitive values. I'm okay at reading this. I can kind of see what's happening. What I should probably do though is squared sum to 1. What I should do is be plotting the okay, let's go. So we've got the degrees. So I should be able to do sine of the degrees. Okay. Does that look right? So if I run this, I should see, actually what I should do is multiply. What should I do? I don't know if I should try and normalize them both to... Yeah, let's do that. I don't know. Let's have a go at that. Just compare Haskell's built-in sine function and see, I don't know how far off it's actually going to be. It's all confusing, because, I mean, it's a bit confusing because the degrees are not actually degrees, you know, they're degrees. Byte degrees, I guess, I don't know. So when I jump here, 350, -251, -43. Hang on, why? There we go. Have I flipped it? Is that the problem? I've somehow flipped sine and cosine. I mean, it's still way off. It's not just flipped. I think it is flipped, but not just. I have flipped it, but not like it's not just flipped. How did I flip it? So let's go to the disassembly. So output is 255 times sine. Okay, yep, and sine and cosine is offset by, yep, Okay, and that corresponds to the C code. If we look at the C code that someone's translated over. So cosine is that. So it's d0 plus 40. That's fine. Yeah, that's fine. And sine is just, you know, indexed by the by the angle that we're at. That's fine. So that's that. So sine and cosine. But then when I go over here and I print it out, it's not that. What? Maybe there's something about jump. Oh, I think jump. You know, I think jump is actually meant to be calculating the angle. It actually rotates the angle before asking what the. Yeah, look, it rotates the angle there. I think it rotates the angle. Yeah, here we go. It takes off OX40 from the angle and then asks for the sine wave. But I mean, that's okay, so that's fine, but it's still, I mean, our sine wave, what we calculate as the sine should be the same as what it calculates out, right? Anyway, we will take out OX40. No, that is what the logic is actually meant to do. Okay, anyway, we'll run it again. We'll see what happens. I mean, we should be calculating the same sine wave as what, I mean, to a certain amount, we should be able to calculate the sine wave similar to what it's calculating. It shouldn't be too far off. Makes no sense. I don't know what the hell it's doing. The numbers are similar, actually. Not there, it's not that similar. But there, you can see it's similar to negative 251, negative 251, negative 43, negative 49. Like, it's there. Here it's way off. That was interesting. And we're actually jumping off this thing. That's what we want. We actually do want it to jump off that thing. So we want to come up here and then if we jump, we actually want it to go backwards. Like that. We actually do want that to, something like that to happen. But we do want to be able to stand on the ground and jump up instead of jump to the left. Seems like the axes are flipped. Yeah, it does seem like that, and I don't understand why. If D1 less than 0, then we do that. Like that, it looks like we just negate it. Is that what it's doing? That looks like it might be just negating. Wait, it's not negating it, that's it's ORing with it, so it's setting it to be large. I don't know. Oh, because oh, I see. So if it's negative, then it wants to keep it negative, so it shifts it across right, but then keeps the, keeps the flag. Yeah, exactly. So it's yeah, exactly. Yeah. Yeah, that makes sense. Okay. which I think Haskell will do. If you shift to right a integer, like a negative integer, it actually shifts it the right property. So if you do, by default, like, so if I had -1, whoops, I want it's int 8. There we go. So if you shift it to right 8, I don't think we need to do that because Haskell, like the int type in Haskell automatically carries over the negative. So I think that's fine. So I think our shift right 8 is equivalent to all of this. And then we just add d1 onto that. So and d1 gets multiplied by the speed, and so d1 was the cosine. There we go, we have flipped it. Yes, we did flip it. I flipped it somehow, which I shouldn't have done because I already had the right code there. I already did have, you know, y use the sine wave. I already had that, so. There we go, we're jumping up. Now we're jumping back, awesome. Jumping forward, oh, that's so good. That's so good, that was so much effort, but it's so good. Not worth the effort, but it's still good. Hopefully jumping up here. No, I didn't jump backwards. I wanted to jump backwards. Because you're meant to be able to, like, be here. There we go. It jumps backwards. There we go. I mean, it's super broken. It's, like, look at that. It's still super broken. But we're doing things. We're going in the right direction. This is so weird. It feels so weird. It's not Sonic at all. But anyway, alright. Okay, I'm over this. I'm gonna finish streaming there. I'm going to commit what I've got. It's good that we got through angles. We've gotten through angles. I'm happy with that. We've gotten through angles. Now we need to actually, like, you know, make it so that Sonic doesn't do this. Yeah, we've gotten through angles. We started on jumping. You know, obviously jumping is super broken, but we've started on jumping. Well, thank you so much. It's always a bit of a mess, the streams, but we're getting somewhere. We're getting places. All right, got angles, starting to get jumping, got some moving. You know, we got the idea of inertia, moving around, acceleration, and so on. So you know, Sonic's physics is coming around. What I would like to do, I'd love to be able to go around the loop. I don't think we're gonna get close to that anytime soon. What we probably should do is work on collision. The collision is super broken. If we work more on jumping and collision, then hopefully we've got something that looks more like a real game. You know, if I can kind of not teleport here, that would be ideal. Like if we actually started working on figuring out what collision means in Sonic, that would be ideal. I'm happy that we fixed the collision where we actually go down now instead of going up when you go downhill. It's good that I noticed that bug. That's quite good. So now I can actually go downhill and actually doesn't go up, like, doesn't look like he's going upstairs to go downhill. So that's good. Okay, so I think next time what I will work on, we'll try and get more collision done. We'll try and work on jumping a bit more so jumping doesn't look like, so jumping goes in the right direction now, which is great. But if you hold down the jump button, you can kind of teleport around the screen and it's not very good. So I think if we work more on jumping and we work more on collision, we'd have a better game. Cool. Any questions about anything I've done today? I know most of it's just been debugging, which is not very fun. Any questions about any Haskell I wrote? I didn't really get to write too much interesting Haskell. The interesting Haskell I wanted to write, I didn't actually get around to, so that kind of sucks. But anyway, let me find someone else to stream. Any questions while I'm trying to find someone? Here we go. Freeman is doing some Code Wars. Actually, I had a go at Code Wars the other day, and it's got some good exercises on there. I want to stream a couple of them. They had some good ones. I'll point out some good ones for everyone, just real quick. We will host Freeman, though, in a minute. Say hi to Freeman for me. So if we go Haskell, I've got some good Haskell exercises up here. So if you want, if you're still learning Haskell, have a look at this thing. It's pretty cool. This isn't actually showing it. I want to see the actual exercises. They are listed somewhere. Don't make me log in. There you go. This will probably be good. Do I have any? So it depends on what Haskell, what UI you want to use, like what type of UI you want to do. Like if you want to, it depends. So I'll show what I did. So I'll show you something that I did on stream a while ago. You can probably find a video on YouTube. I don't know. I think I uploaded it to YouTube. Yeah, I think I did. So I'll just show a quick GUI I made real quick, and I don't know. Let me know what type of Haskell UI, like what type of UI you're after. I'll show one type of UI, which is like basically making like a tiny UI for a game. It's not very good. If you look down below on my page, you should be able to find a YouTube link. So this is a UI I made real quick, and so this is like this is a game of tic-tac-toe. And so this is actually like the good thing about this library. This is called Gloss. Good thing about Gloss is that it's like an algebra. It's based on like the algebra of like it comes up with like its own algebra of like graphics. And so you're basically able to take like I said, draw a line from here to here, draw a line from basically like the top left to the bottom right, draw another line from bottom left to top right, and then you can kind of just add those together. So you just say add those two lines together and you get a graphic, and then I can kind of position them around. So then I can say take that like composed graphic together, move it over here, make another one of them, move it over there, and so basically you got like a composable algebraic GUI library, which is really, really cool. And if you're just trying to make like GUI that to like kind of, I guess, like draw diagrams and things, or like trying to plot things, this is a really good library for it. But this isn't actually like for writing a GUI app. So it depends on what you're trying to do. Like if you wanted to make something that you ship off, like you won't be able to copy and paste things into this, for example. Like it doesn't have the idea of widgets. It's got the more idea of graphics. So yeah, so that's one library. There's FLTK Haskell. I think FLTK Haskell, is it? Here we go. This one, I've heard these are really, really good, really easy to use. I haven't actually used it very much, but it seems very good. So I'll check out this library, FLTK GUI. It looks really, really good. What do I mean when I say algebraic? I don't know if that's the right, I mean, I can talk more about this. I don't know if it's really the right type of GUI that you want though, but basically you've got the idea of pictures. You've got the idea of pictures. And so a picture is like a line, so you draw like a little path, or you got like a circle, and you got a bitmap. And if you look down here, the algebra is basically monoid. So you got like a monoid of picture, and that basically means if you had two polygons, you can use the monoid to append those two polygons together, and appending just means draw them together, just draw them over top. So the algebra, so what I mean by algebraic is basically you've got the algebraic property of associativity and like the identity element for a picture. There's a couple other things in there as well, but that's basically the core idea. You've basically got pictures and you can append them together. And it's just really easy to work with because you can append them, and you've got translation, and it's all associative in that. And so you've got a couple of algebraic properties around pictures, which I think is really cool. Like it's just a really nice. The identity element is just a blank picture. It's just blank. It's just yeah, blank. It's the blank picture. So it just draws nothing. Yeah. So I really like it if you're trying to like draw diagrams or trying to like basically make a little thing with like a little button here, and basically like a little game or a little like just interactive way to do things. Gloss is really, really cool. It's really nice, and it's got like a lot of helpers around. There's like IO interacting kind of like it's basically you say this and you give it you basically give it a couple of functions. You give it a function that handles ways to draw a picture, way to handle input, and then I'm not sure what that is. Cool, like to take the display control. I don't know what that is. But anyway, you've basically got these two things: way to display the world and a way to kind of update the world based on events that come in. So it's basically like if you've used, is it React? If you use React, it's the same. Can I do a use Haskell as a CLI tool stream showing how to use Haskell for scripting tasks one day? Sure, yeah, I'd like to. I do use Haskell for scripting a lot, especially at work. We use it a lot. I used to work as SRE. I'm technically not SRE anymore, although a lot of SRE tasks still come to me. But I worked on SRE with another person, Richard Wallace, and he is really into Haskell as well. I mean, he knows Haskell really well. I shouldn't say he's really into it. He knows Haskell a lot, and we use it for scripting. So yes, I should do something like that. Use Haskell as a CLI tool because we have a lot of tools inside Atlassian that are CLI tools. I mean, it's basically our team has a lot of tools that are Haskell CLI tools. So yes, I should do a stream like that. What I was going to say is that there is some cool exercises on Code Wars for Haskell. For example, this one. This was a really good one. This one, you have to prove that if you have an even number, and then you want to add where is it? I don't know if they've got it. Here we go. If you have an even number and an odd number, then you get back, like if you were to add them, you get back an odd number. And so you have to prove that in Haskell. It's really, really cool. Really, really good exercise. Yeah, I like that one. So I had to go a couple of these, and there actually are a couple of good ones on there. So if you're looking at like doing some advanced Haskell, like there's some good ones on this. There was also, I don't know if you saw it just here, it was one function, many arguments. So the idea was that you write polyadd and you make it take many arguments. This one's a bit tricky. This is just, if you look on Code Wars and just, yeah, I'll link it here. So which one? I'll link both of these. Just 1 second, Code Wars. Yeah, so I'll link both of these. These are good ones. So there's one function, many arguments, which is basically writing out, like, I guess, yeah, I don't know, it's like writing, it's tricky. It's writing polyadd, but it can take as many arguments as possible. You just keep taking arguments, which is really interesting. It's a really tricky one to do. It is, I actually did, there's a couple of different ways to do it, but I did one where I only used type families. The only extension I enabled was type families. You do have to enable an extension. There's definitely no way to do it in Haskell 98, but yeah, it's fun. I did it using only type families, which I was pretty happy about. And let me just link this one. And that's a fun one to do as well. I mean, these are both really tricky. Like if you can't get these, that's completely alright. Like they are tricky ones to do. This one's actually got a prerequisite that you do this one as well, that you prove commutativity of addition, that's a tricky one as well. They're all really tricky, but they're fun. So if you're kind of like intermediate Haskell level and you want to try and do a little bit better, then have a go at that. But we are going to raid Freeman 42X, so say hi to him for me. I will, I guess I'll try and upload this stream to YouTube, and I will commit the code, and next week we'll try and work more on collision and jumping. So get prepared for that, because that's going to be some more tedious, I guess, debugging of code, I guess. So thanks for everyone coming in today. Say hi to Freeman for me. I've been talking to Freeman quite a bit recently. Yeah, he's good. So, alright, I'll see you all next week. Thanks for coming in.